Hey folks, welcome back to Chapter 5, our discussion about forces, dynamics. This video, we are going to look at, I guess it's a continuation of F net equals ma, but it's unlike the 3 videos on Newton's laws where there was tons of variation. This one I think you'll like a little bit more again. There's a little bit less going on. We are going to look at 2 different quantities. One of them called momentum, and then another quantity called impulse. So momentum, we'll start with that, is a vector. Remember that any vector quantity means that it has both a size, a magnitude, so a number, but then direction is also important. We will see that velocity is part of momentum, and since velocity was a vector, the whole like positive versus negative, left and right, that was important to catch with velocity. It will also be important to catch with momentum. Now, one of the reasons I never gave you textbooks this year for Physics 11 was that in your textbook, I'm just going to take a little aside here. In your textbook, in the section dealing with momentum, the authors of the textbook talk about how we sometimes use the word momentum to talk about sports teams. How when they get on a roll, we might say that a sports team has momentum, and we do talk about that all the time. The authors of your textbook somehow mention that when a sports team starts rolling and we say they'd have momentum, that we call it Big Mo. And I don't know about you, but I've played on a lot of sports teams, I've coached a lot of sports teams, and I have never mentioned having Big Mo on our team side. I have no idea who Big Mo is, but I've just never met this individual. So one of the reasons I don't give you guys textbooks is nobody would read them, and then even if you did the stuff that was in there, it wouldn't really make sense. Anyways, random aside, moving on. Momentum, not Big Mo, although that leaves me with a really interesting mental picture while I have this discussion with you. I'll come back to that picture. The symbol for momentum is a lowercase letter p. You should technically have the little arrow on top. We often don't put the little arrow. All vectors should have the arrow, but we tend to drop them in Physics 11. And the equation for momentum, which is a lowercase p, again, a weird choice, is simply an object's mass multiplied by its velocity. M times v. Nice and easy. And if you think about the units, in physics, we like to measure masses in kilograms. We like to measure velocities in meters per second. So the units here, they're kind of weird, but it's what they have to be if we're multiplying a mass by a velocity. The units are kilogram meters per second. So let's try a really easy example here. Find the momentum of a 75 kilogram student walking negative 2.3 meters per second. That probably just means to the left. I don't know, maybe it's somebody moonwalking down the hallway too. What kind of momentum would they have? Maybe you could imagine if this person bumped into you, you would be experiencing that momentum. And you would maybe have an idea of what that would feel like. Some larger student bumping into you who's fast walking down the hallway. So P is simply M times V. It is literally this easy to get us started in this video. 75 times negative 2.3. Round to your 2 or 3 sig figs, we get negative 173 kilogram meters per second. That is the momentum that that student has with their mass and that velocity. Now I want to go back and show you a picture just that kind of goes with this discussion. So we're talking about momentum being all about masses and velocities, and we've got this little guy playing some rugby. Probably not a huge momentum, just because he doesn't have a very big mass, and he's probably not running that fast. So he'd have some smaller momentum. I don't think anybody would worry about this little kid running into them. You wouldn't experience that much momentum if they bumped into you. But what if this kid grows up and gets bigger and turns into this fellow? This is Nakai Penny. He is a Penn High grad, really great kid. I taught him when he was in grade 10 and grade 11. He is a professional rugby player now. Plays in Seattle, I believe, in a professional rugby league. When he played for the Penn High rugby team, they actually had a pretty good team because the team was Nakai. So I just wanted to show you this picture. It came from a local newspaper years ago. I want you to count the number of Penn High players in the picture? 1, Mr. Nakai. I want you to count the number of black jerseys in the picture. 1, 2. This kid, that is a face experiencing momentum. Look at that. He knows all about Nakai's momentum, right? Bigger mass, bigger velocity. Ooh. So there's 2, 3, 4, 5, 6, 7, 8, and there's a 9th black jersey right there. So 9 players from the other team and Nakai is in there just destroying this poor guy. Nakai's a really nice guy, really nice kid when he was in high school, which was great for everybody else. But you put him on a rugby field, he was a destroyer. So there's a cool little picture just showing you what bigger momentums might feel like. And if you're feeling big momentums, you might end up with that face. Okay, let me show you a second example. This looks really confusing. What's the momentum of a car going 72 kilometers an hour? Vectors, right? 18 degrees north of east. And the car's accelerating 4 meters per second squared north. Now there's a lot going on there, and you might be looking at that question going, oh my gosh, I don't want to deal with all of this again. Like resolving vectors, do I have to break down the 18 north of east? What do I do with the acceleration? Is this kinematics? And the answer is no. The equation for momentum, maybe I should ink it in at the top there. Momentum is simply P equals m times v. So you plug in your mass, 1,550 kilograms. You plug in your velocity in meters per second. That's what that little division by 3.6 is doing. So you got to catch that. You simply multiply those two things together. There is no angle to worry about. Actually, there is. We'll see how to deal with that in a moment. But there is no acceleration, right? At that instant, while it's accelerating, I'm not going to put that in there. At this instant, the momentum is 31,000. We'll call that chemistry rounding. There's your physics rounding, 3.1 times 10 to the 4 kilogram meters per second. And then the cool thing is we can simply take the direction and just tack it back on to the final answer. So you don't have to worry about in this lesson at any point resolving vectors or even really dealing with them. If you see velocity at an angle, then you've got momentum at an angle. Life is good. The whole accelerating at 4 meters per second squared north, that is the instantaneous momentum. If we were to look at this thing 3 seconds later, now it would have a different velocity, so it would have a different momentum. But we're not asked to worry about that in this question. So this is just what's the momentum right now. We don't even worry about the acceleration. Done. Now simply calculating m times v all day long is boring. We quite often want to find an object's change in momentum. And if you think about an object having a change in momentum, mass times velocity, it's probably not the mass that's changing for the object. It's probably more a story about the velocity for that object changing. So remember that when we find the change in a quantity, it's always final minus initial. So if we want to find the change in momentum, you could just call it PF minus PI, which is your mass multiplied by the final velocity minus the mass multiplied by the initial velocity. And then we can just sort of factor an m out of there. We end up with that equation. This equation right here is one that we use a lot. So your change in momentum is equal to an unchanging mass multiplied by some change in velocity. So I'm going to put stars beside that because that's really commonly used, although you don't see it in that form on your formula sheet. On your formula sheet, you're going to see this form. Delta P equals m delta V, where we take the change in velocity and we write it as just that delta V. So that's the formula sheet version. The one with the stars is the, hey, let's actually use the equation on paper with some numbers version. And let me give you an example. We'll try this out. What's the change in momentum for a baseball that was going 24 meters per second forwards? Maybe somebody's pitched it, and then the batter hits it, and it leaves going 36 meters per second backwards. So we're going to use this change of momentum equation, but we're going to go with the VF minus VI version because we do have, we're going to go with that one. We do have two separate velocities. You do have to be very careful when you're dealing with these velocities, the final minus initial, that you catch the direction. 24 meters per second forwards is going to be a positive 24. And then the baseball that leaves at 36 meters per second backwards, that has to go in as a negative. So I need you in this lesson to be very cautious about whether things are moving with positive or negative velocity, because if you miss those negative signs, it's going to totally throw off your final answer. So delta P equals m delta V. There's your mass in kilograms. Kind of nice. We've had a physicist measure this as opposed to a chemist. The final velocity was the negative 36 backwards, minus the initial velocity, which was that positive 24. And if you throw that in your calculator, you get negative 8.4 kilogram meters per second. So there's an example showing you how to find an object's change in momentum. Pretty darn easy. Now let's switch over to another quantity called impulse. Impulse is a vector as well. There is no symbol for impulse. We don't use a capital I because that's the symbol for current, which we'll see in chapter 9 when we look at electricity. You should technically, if you're finding impulse, write down the entire word impulse. If you want, for physics 11, I'm okay if you go with like IMP. So I'd be okay if you did that for impulse. Don't use just a capital I because we don't want to confuse things with current. But if you want to at least go shorter than writing the whole word impulse, go with an IMP. The equation for impulse is force multiplied by time. So your force in newtons multiplied by how long that force was applied for. And quite often students look and they go, oh, Mr. Heinrich, I know what the units have to be. They have to be newtons per second. But that would be if you were dividing a force by a time. Here we're multiplying, so the units are actually Newton seconds, which is kind of weird, but that's what the units have to be if you've got a force multiplied by time. Now, I'm not even going to show you an example with impulse because it is literally as easy as multiplying F times T. What I want to show you is how does this tie into chapter 5? Well, we've got some forces here. What if we look at Newton's second law, F net equals ma? In that equation, you can say that acceleration is a change in velocity divided by time. So what if we swap out acceleration and we insert this delta V over t? And then this equation, it's fine, it works, but let's make it flat. Let's multiply both sides by t. We end up with that. Now I'm hoping you can look at that equation and go, oh, whoa, because there's something kind of cool there. That is telling you that Ft is impulse. And m times delta V is change in momentum. Those two things are the same. And it's going to take you maybe a few seconds to wrap your head around that. Impulse is exactly the same as the change in momentum. It's got this big fancy name. It's called the impulse momentum theorem. What it means is you can't have an impulse without a change in momentum. You can't have a change in momentum without an impulse. Those two things are going to happen together all the time. What's really, really cool for us in physics is that if you want to find the change in momentum for an object, you can use m times delta V, or you can use F times t, because either side of that equation is the same thing. And the flip side of that, if I want to find impulse, I should technically use F times t, but I can also cheat and use m times delta V because it's the same. So it's kind of nice. You can find change in momentum with this or with that. And the flip side, I can find impulse with this or with that. Like either side of the equation can be impulse, either side of the equation can be change in momentum. You get to sort of cherry pick from whichever side of the equation will work for you. So let me show you an example where we do a little cherry picking. So let's try this one. We've got a volleyball player applying a force to a volleyball, and that gives it a change in velocity. I would like us to, off the start, let's find impulse. So you go to your formula sheet, you say, okay, Heinrich's asking us to find impulse. Impulse is equal to F times T. And then you look at this and you go, oh, crumb. That's not going to work. We've got a force. We got that. It's negative 75. But they don't give us a time. What the heck? Well, remember we've got that impulse momentum theorem where impulse is equal to momentum. So if this doesn't work for me, because I don't know the time, then we can cheat, and I'm saying that in air quotes, we can cheat and we can use m times delta v. So either one of those equations will give us impulse. The first one didn't work because we have the force but no time, but we do have a mass, we do have a final velocity, we do have an initial velocity. So let's use that one. 0.85. Final velocity is negative 6.8 minus the initial velocity was 4.5. And if we bang that out on the calculator, sorry, I'll shift that over. 6.8 minus 4.5. There you go, negative 9.61. Now there's the size. What about the units? What we should do, even though we cheated and we used change in momentum to find impulse, which is okay because those two things are the same, if a question is looking for impulse, then you should go with the units on impulse. So let's throw some Newton seconds on there. So there's part A. We kind of got to cherry pick, which was kind of neat. Part B, there's one last thing we don't know. We talked about this issue up above. Let's find time. So the cool thing here is now we can go back to that initial equation if you want. You can say impulse is equal to F times T. We do know the impulse now. I'm actually going to throw in the full number. I think it was 9.605. We know the impulse. We know the force was negative 75. And we can really quickly solve for T. T equals, divided by negative 75, 0.128 seconds. So there's your two answers. So nice example showing you that you can sort of cherry pick. You can use either side of the equation. Life is good. And we'll finish off with one final example here. We are looking for the final velocity for a brick that has an initial velocity of 22.5 meters per second and a net force of negative 15 newtons. Act on it for 19.5 seconds. I want to show you the old way of solving this, and I don't even know if you need to copy the old way down. The old way still works. This is not a bad thing. So don't think old means bad. This is just the alternative that we learned earlier in the chapter. What you could do is you could treat this as an F net equals ma, where you plug in the net force, you plug in the mass, you solve for the acceleration, and then you run some kinematics, and you get a final velocity. That's totally fine. There's nothing wrong with that. And if that's the way that your brain wants to interpret this question, if you see it on a quiz or a test or university, and you do it that way, it's fine. It's fine. Nobody's going to fault you for that. What about the new way? Again, new doesn't necessarily mean better. It's just the way that we've learned this lesson. If you look at that question, there's a velocity, a mass, an initial velocity, a force, and a time. That actually is listing every single piece of the impulse momentum equation. F T equals m delta V. And I'm just going to go to the expanded version. Remember, we said we find change in momentum with that version of the equation. What's cool here is I'm looking for a single variable. I'm not asked for just the impulse. I'm not asked for just the momentum. I'm looking for a single thing in that equation, and that is VF. They give me the mass of the brick. They give me the initial velocity of the brick. They give me the force. They give me the time. So what's nice is this impulse momentum theorem, if you're asked to find a single thing, a single variable, not a whole side of the equation, but just a single variable, then you can actually use the entire equation and in one shot at once. So I could simply go negative 15 times 19.5 equals 8 times VF minus 22.5. You've got some options in terms of the algebra here. You could distribute the 8, multiply it by VF, multiply it by negative 22.5. I would actually divide out the 8. I think it's a bit quicker. So I'm going to do it that way if that's okay with you guys. Negative 15 times 19.5 divided by 8. Negative 36.5625. 625 equals VF minus 22.5. And simply add 22.5 to both sides. Sorry, I won't show it. I'm just running out of space. Plus 22.5. Hey, look at that. There's the answer right there. Same as the old way. Negative 14.1 meters per second. So I like the new way, just it's a little bit quicker. The old way was like a F net equals ma, then you had to make a VIF-DAT list, then you had to run some kinematics, impulse momentum, kind of a one-shot deal. So it's a little bit quicker. Maybe we should call it that. There's a slower way and a quicker way. Again, not that slow is bad and not that quicker is better. So there is impulse momentum. Give the homework a try. I think it's numbers 1 through 12. Just check your chapter outline for that. And hit me up in one of the Zoom meetings if you would like to go over any of these questions, or fire me an email, or look at the full solutions in the Chapter 5 solutions folder on the website, or even hit me up with an email and ask me to do an additional Zoom meeting if you want to actually see me do some inking and writing on the screen in real time. So have fun with impulse momentum. Please join us for the next Zoom meeting, and let me know if you have any questions. Take care.